So the first force we're going to talk about is universal gravitational force. It's Newton's um, really big push towards a new kind of understanding of the universe. The universal gravitation says, and by definition, the word universal gravitation was able to combine what we know happens on Earth to what we understand happens in the universe. Normally, before Newton's time, we believed that the force of gravity that we experience on the Earth was entirely different to the same force of gravity that we experience in the universe. The interaction between the Earth and the Sun was believed to be a completely different force than the interaction of a ball near the surface of the Earth. So, it wasn't until Newton coming up with this idea of universal gravity, and that's why it has in its title universal gravity, did we start saying, hey, look, those forces are actually the same thing. They're an interaction between two massive objects, and those massive objects produce this force of gravity, if you will. So from there, we start, like I said, getting more of an understanding towards how the universe works. I'm going to go ahead and write up the equation. Now that's the equation for it. Now, in a real physics class, we would add something else to it. We would add this. Now, you guys already know from, hopefully you remember your component forms, and that this is just telling me that this is in the direction of r. Okay? And because it's in the direction of r, there's actually going to be a negative sign in front of this term. Cool? And let me explain why. So if I've got two massive objects. I have massive object 1, massive object 2. Okay? And when I mean massive, I don't mean big. I mean having mass, having inertia. Well, the radius that we're talking about here, this r, let me darken that a little bit. This r squared under there, the radius that we're talking about starts from the center of one massive object and goes to the center of the other massive object. Okay, that's the radius in which we're talking about. Well, so initial position, final position, this object is exerting a force on this object, but which direction is that force being experienced? Where is that vector that's associated with this force? Because it is a force and it has a direction, obviously. So in what direction is that force? Well, we know from experience, if I were to take an object and I were to drop that object, we know that the force is in this direction. Well, the radius is in this direction. It comes from the center of the Earth towards the center of that object. So the force is in this direction and the radius is in this direction, hence the negative sign. It's in the opposite direction of the radius. Okay? So we know that there's a gravitational attraction in this direction. Okay? So that's why there's a negative sign. Now, a couple of other things that are real important to talk about are these ideas of mass. Well, we've already come up with the idea of inertia, thanks to Galileo, that these objects have these natural tendencies for an object to move or to stay at rest. That once, this inertia is this property that resists changes in its motion. So how does that translate to being a component of force, like we did with gravity, gravitational force? Well, we've already introduced this idea that inertia is mass, that those things are identical to each other. So it wasn't very hard for Newton to sell this idea that this resistance to change that we call inertia is also equivalent to the amount of stuff it has, basically. How much junk it has in a small container. And that container being basically molecules and atoms. So he's like, well, that amount of junk in there is a big chunk of this gravitational equation. So how much junk this has and how much junk this has affects the strength in between them. Okay? So we're already taking a concept, this inertia idea, which is this resistance, and we've been measuring inertia for quite a long time, and we're just taking it and tweaking those numbers, because we've already assigned it, to fit my universal gravitational laws. So this mass is mass. It's inertia, but it's not. It's not talking about its intrinsic property to resist changes in motion. It's talking about how much stuff is in there. So it's the same number, it's the same unit, but philosophically it's not the same thing. Okay, if that makes sense. But because we already have it in our vocabulary, we just simply are going to be using it back and forth in this equation. Cool? So gmm over r squared. As a matter of fact, when Newton originally derives this equation, he's more concerned with mm over r squared. Okay? The big value here, g, is not really determined. I mean, it's not really determined with a high degree of accuracy until well past Newton's time. He has an idea of what that number is, but it's not until well after Newton did we start developing experiments to accurately measure what g is. Okay? It's one of those universal constants. Now, the other thing that's really interesting is we end up getting what's called the inverse square laws out of this. 1 over r squared is what we call in physics an inverse square law, which means that everything in the universe that it falls off at infinity, but everything in the universe experiences it. And it kind of, here, let me draw you what the inverse square law looks like without having to go too far. So if I were to say I had an object with a certain amount of mass at a point, that the gravitational attraction that this object exerts on every other piece falls off something like this. And this, there's my eraser. This attraction is stronger at this point and weaker up here. And as a matter of fact, the further out it goes, the shallower and shallower it gets until you get to infinity, where it turns into 0. Well, where's infinity? So that's why it's an inverse square law. That by definition is really, really strong close to the object, really, really weak farther away from the object. Okay? So inverse square laws end up in another equation that we're going to talk about next, which is Coulomb's law. But we just give them this title of inverse square law. That 1 over r squared is what's called an inverse square law. Okay? So mass 1, mass 2 over r squared, g, which is this universal constant, negative because the force is in the opposite direction of the radius, because I do have a direction associated with it. Okay? So that is Newton's gravitational force. So it requires there to be two masses in an area. Okay? And there requires a distance to be in between those masses. Now the really cool thing about it is Newton's like, well, we can determine some of these things. We can determine the value of big G by experiments that have already been performed. He says, well, if this is the mass of the Earth, this M2 over here, then this would be the mass of the ball that I hold above the surface of the Earth. This, in this case, this eraser. And this universal gravitational constant, this G, is universal. So at the surface of the Earth, that G is the same as if it was in space. So, wow, okay, well we've got this mass, we've got this universal constant. I can measure the mass of this. But what about r squared? Well, we've already known about r squared, the radial value of the Earth, for a long time. It's not Archimedes, but I can't remember his name. Aristophanes, I think, has already determined the radial value of the Earth. He was able to determine the circumference of the Earth by using shadows and a distance in between them. He was able to say, "Hey, look! If I knew these angles, I could determine the radius." So we already had that number in Newton's time. So we had these numbers in Newton's time. We knew kind of what the mass of the Earth was. So we were able to come up with this idea that this, if it was close to the surface of the Earth, would be some sort of constant. Well, let me restate some of these things. If the mass of the Earth remains constant, okay, the mass of the gravitational constant in the universe remains constant. By definition, it's a constant, so it should. And if the radial value of the Earth is a constant, then this number would be a constant. And if it's a force, what are the units of all of this? I'm circling g, m, o, and r squared. Well, if it's a force, we know force is equal to mass times acceleration. This turns out to be an acceleration. So ma, okay, that's equal to a force. But when we're talking about gravity near the surface of the Earth, on the planet Earth, what acceleration are we talking about? We're talking about the acceleration due to gravity, g. So this big G m1 r squared is equal to the acceleration due to gravity near the surface of the Earth. This radial value has to be the radius of the Earth. At the surface of the Earth, that r is relatively the radial value of the Earth. I mean, if I were to hold up this eraser, there's very little difference between its r value towards the center of the Earth and the radius of the Earth. It's only until we get in higher and higher orbits that we experience a different r value. And as a matter of fact, we know that. I'm here in Denver, where the acceleration due to gravity here is about 9.801, I do believe. And if you went to the sea level, like Florida or South Carolina, you're looking at the acceleration due to gravity to be 9.81. And the reason that is because I am slightly further away from the center of the Earth, so my acceleration is slightly smaller. But 9.8, 9.8, I mean, they're almost identical. It's not until you get some serious altitude, like up in the space shuttle, where the acceleration due to gravity is something significantly different. And it's not 0. It's about, what, I think it's almost 8. I think it's 7 points. I think it's like 7.8, 7.6, somewhere in that range. That the acceleration due to gravity is at that point, and you're talking miles and miles above the surface of the Earth. So it's not until you get some real significant difference from where you are compared to the radius of the Earth do you experience a slight change in that acceleration. So we can determine g. We have determined g historically. I mean, Galileo had determined g, not very accurately, but he still did it. So from this value of g, we were actually able to determine this universal constant. And then a few experiments come along later that was like, all right, we can do a better job of determining g. So that happens later in history. So this is an introduction of Newton's universal gravitational forces. I'm going to talk about what actually these mean. Some of these are things. What is that all about? And then we're going to talk about Coulomb's law.